Welcome back to question 2 of our series where we learn how to test hypotheses for a single mean. This time the question reads, suppose that the mean cholesterol level for males aged 50 is 241. An investigator wishes to examine whether cholesterol levels are significantly reduced by modifying diet only slightly. A random sample of 12 patients agrees to participate in the study and follow the modified diet for 3 months. After 3 months, their cholesterol levels are measured and a summary statistics are produced on the 12 subjects. The mean cholesterol level in the sample is 235 with a standard deviation of 12.5. Based on the data, is there statistical evidence that the modified diet reduced the cholesterol? Let's begin by stating our hypothesis. We'll say that our null hypothesis will be mu is greater or equal to 241. So this is the average for the entire population, and the alternative hypothesis, which I'll denote as H sub A, has to be the opposite. And given that our alternative hypothesis is less than 241, we'll be using a one-tailed test as opposed to a two-tailed test that we used in the previous example, and it will be the lower tail test. Let's also write down what we have been given. We've been told that it's a small sample size, 12. Remember in the previous example it was 50, which was greater than 30, and so we used the z-test. This time, because this is less than 30, we'll be using the t-test instead. So it's 12 patients, and we've been told the average, x bar, is 235. The standard deviation for the sample, which we denote as s instead of sigma, is 12.5. Remember, we use the symbol sigma only when we're looking at the entire population's standard deviation. We'll use the same formula as before, where, remember, we were using the z-test before, but the t-test uses the same formula anyway. X bar minus sigma over s over the square root of n. It's the same formula, just a different table that we obtain our critical value from. Now, substituting these values, remember it was 235 minus 241 over s, which is 12.5, divided by the square root of 12. Let's go ahead and use our calculator. 235 minus 241 divided by 12.5 divided by the square root of 12. And we get negative 1.66. Let's write this number down. We have negative 1.66, and this number is referred to as our t observed value. And to prevent further confusion, if it's already confusing you, we're not doing the z-test, we're doing the t-test because n is less than 30. So t observed is negative 1.66. We'll be using this value along with this table to find the t critical value, and we'll compare the two. So if we look here, notice that the numbers are not negative. That's fine. This is negative. So just look for the positive version. And we have a one-tail test. In addition, it's an alpha level, a significance level of 0.05. The way I determine that is because they don't tell us the significance level. And if they don't, just use 5% or 0.05. So looking at this column, we also have this column called df. That's degrees of freedom. To calculate the degrees of freedom, we say n minus 1. Our n value is 12, so 12 minus 1 is 11. So 11 and 0.05, it's 1.796. Let me just circle that, 1.796. Therefore, t critical is 1.796. Because this number was negative, we should also make this negative. And to show this on a t distribution, negative 1.796 will be right over here. Zeros in the middle, of course. Negative 1.796. And here will be our rejection region. The rule is that if t observed is greater than t critical, and it is, notice that we have negative 1.66 is greater than negative 1.796, then you do not reject the null hypothesis. So in this particular case, we cannot reject that the average is greater or equal to 241. To interpret that differently, we don't have enough evidence at 0.05 significance level to conclude that the average cholesterol level has been reduced because of this diet. That's our answer for question number 2. If you'd like to see the answer to question number 3, some more practice, make sure that you watch question 3 of the series where we cover this solution. Hope to see you soon.